Let's think about our model for the linear regression equation in terms of distance from each y value to the mean. So suppose this is our regression equation, and let's think about that this is y, this is x. So this is one that I've estimated with the sample. So this is y comes from the y-intercept, the slope, each x, and each residual. Okay, so the mean of the y's is roughly here, and the mean of the x's, let's suppose that I have, is here. And we know that the regression line goes through the mean. So now let's break down what's going on with some individual data points. So suppose this is one of my data points. Let's suppose this is a data point, and let's suppose this is a data point. So with those data points, that is not exactly where x bar is, but I'm just doing this to highlight the meaning of several different terms. Okay, so one of the measurements we're going to think about is y minus y bar. So each actual y and its distance from the mean. So the difference between y1 and y bar is there. The difference between y2 and y bar is here. And the distance between y3 and y bar is there. So each of my pink colored bars represent those distances. So if we take each of those distances and then added them up, this is my sum squared total. So what it's telling me is about the amount of total variation that's existing in my dependent variable y. So now let's look at another aspect of this model and what's happening. Let's choose a different color. Let's suppose we pick something completely different. So now let's look at each prediction. So this one is the actual prediction for x1 because it's on the line. Here's the actual prediction for x2 because it's on the line, and here's the prediction for x3 because it's on the line. Okay, so if I measure the difference between each prediction and the mean, so where is that? The mean, that is this distance. It is also this distance, and in my last case, it's this distance. So my green brackets are each y forecasted minus y bar. If I added all these up, this would represent what we're calling sum squared explained, or SSE, or explained sum of squares. So why is it explained? It's saying that green bracket is the measurement that the model is telling me is how far y is away from y bar given that x. So the model is explaining that amount of variation, whereas the actual y's compared to the y bars is the actual variation is from my sum squares total, my SST. Okay, so now let's look at my first case with the green bracket and the pink distance. Let's put a little bracket with it. As you can see, out of the sum squares total on each data point, part of it is explained by the line and part of it is unknown. So I'm going to use a different final color. I'm going to say this color. In other words, this gap, we don't know why there's that gap between the actual data point and the line. In the case of my next one, the gap between the data point and the line is this. In the case of the last one, the gap between the data point and the line is this. So in each of these cases, we're going to think about what was the actual data point versus what I forecasted for that data point, the prediction. And if I add those up, these are the sum of the squared residuals. So this is important because if we think about the following relationship, out of all the total sum of squares, or how much the y variable has dispersion or variation, it's broken up into two pieces. The piece that we can explain added to the piece that we can't explain. And so looking at the first data point is the easiest visually. The whole variation was the pink, and if I took that green bracket of what I explained and then added a negative of the little blue bracket, I would end up with the pink bracket. So the